Welcome to video 10. This video is going to be why we started off with non-inductive coils. Some time ago I wrote a brief document. There's not many pages in this document, but does science truly understand electromagnetic induction? Now there's a huge difference between electromagnetic induction and non-inductive. If you were to talk non-inductive and then say induction, it's contradictory. One means the opposite, if you like, to the other. It's, as I say, it's contradictory, but if we were to break it down, again the purpose of this video series, break it down to the smallest possible pieces, you'll see something pretty amazing. Now I run through a few definitions in there, run through a few little problems, even with the MIT example of the coils, the magnetic fields, and we get to this image here. This is the typical definition and the typical idea of a non-inductive coil. The terminals here, one negative, one positive. The current would flow up the coil and then back down the coil. The arrows there you can see are in opposite directions, and from our experiments in previous videos we've seen exactly what this arrangement does. Now this is termed as non-inductive. Now if you were to think about and go down to the wire level down here and look at the magnetic fields and look at the curl of the magnetic field around the wire, and then compare it to its neighbor, you get a pretty interesting effect. Now on that, if we were to take this image, okay, now this is effectively, it's the same coil, but we've extended it and we've taken the terminals out here and the terminals out here, but the arrows, if you look, the arrows on the wire are exactly the same. So that is telling us that each wire on this coil here, on this former, each wire is equal and opposite. There is no difference between this, between the wires. There is no difference between that and that. The only difference is we have one end folded back on itself, and here we have a set of terminals coming out. But at a wire level, it's exactly the same. It's exactly the same process. There's no difference. Now, again, if we were to go down to the wire level, what we see is we see this. Okay, see the arrows? So one arrow is up, one arrow is down, magnetic fields opposed. Okay, and that's the same in both examples. So if it was non-inductive, if we have a terminal down here, a terminal down here, current runs up, comes back across, and then comes back down this way. Magnetic fields, okay, the curl of the magnetic fields oppose each other. It's exactly the same. So does science really understand magnetic fields? Does it really understand induction? We have terms that effectively are contradictory, yet in a transformer, any one point in time, if you were to take a snapshot between the input coil, this one over here, and the output coil, this one here, this process here is exactly 100% exactly what you see. So non-inductive is not non-inductive at all. Okay, that's the whole point of this video series. I just want to go through and just show very quickly an electromagnetic induction equation. Okay, electromagnetic induction. This is a very simple calculator that I've built. Radius, so say for example we have a circular coil. Radius of that circular coil is roughly 5 centimeters. Number of turns in the coil is 200. Theta, this is the angle, or at least this is the difference of magnetic flux that's cutting the coil. So if it's at 90 degrees, we put 0 in here. 0, 90 degrees. If we had, say, maybe a 10-degree cut where the coil was not being cut properly, not being cut by the magnetic fields themselves at a 90-degree angle, we would change the angle, and that does make a difference. B initial, we're going to start with 1. B final, we're going to start with 10. So I'll just explain very quickly B initial and B final. So this is the d phi dt. Okay, so B is the phi, is the magnetic flux. At the initial value, we're going to start off at 1 Gauss. The final value, we're going to finish off at 10 Gauss. And we're going to do all that over 1 second. Now the resistance here of the 200 turns is 3 ohms. Okay, we're just guessing that, we're just using that as an example. Could be 300 ohms for all we know. Now the resistance, should be noted that resistance is different from impedance. Resistance in ohms probably really should be impedance here. Obviously this depends, impedance depends on the frequency, which would be the delta T, 1 over F, 1 over frequency. So this could change dramatically. So be aware, this is, at this stage we're just guessing, we're guessing a 3 ohms DC. Alright, so with these particular figures here, we get 14.137 volts. Now EMF is the quantity, and the quantity is measured in units of volt. Okay, so some people say EMF is not volts. I argue those people don't know what they're talking about. They are one and the same things. It's just that the voltage is how the EMF is measured. Okay, amperes, amperes I. Now at that particular resistance we get 4.71. Okay, let's change that. Let's give you a bit of an idea. Let's say all of a sudden we've introduced a factor of 10 times the resistance, and look at that, our amperes and our circuit changes dramatically. Okay, so something to take into account. So let's go back. This is a pretty interesting little calculator to play with. This is something I built quite some time back. Give me a bit of an idea of the coils and the turns and so on and so forth. Now let's change the radius of our loop. I'm going to keep 200 turns, keep everything else, but we're going to turn it into 50. 50 centimeters is the radius now from 5. And look at that, look at our voltage, look at how much our voltage changes just by changing the cross-sectional area. Okay, because what is it, pi r squared I think is the area for the radius of a loop. So 1413 volts from 14. So by increasing the radius by a factor of 10, we've increased the EMF, the voltage, by a factor of 100, from 14 to 1400. It's huge, it's horrendous. Something to really truly think about, people. I see some people with very small cores. Now there's nothing wrong with that, but you narrow the window, if you like. You narrow the window on a successful result by using a very small core. Now you'll see I've made a mention through this video series several times. You'll see most of my coils have lots and lots of turns on them. Most of my coils have lots of turns on them for this very reason, so that I can get the voltage up. Okay, but not too ridiculously. I mean, you know, I don't have 10,000 turns. I might have a couple of hundred or so turns. I think from memory, I suggested starting off at 40. 40 is a pretty reasonable number as well. But again, this is a little bit of a juggling act. You've got to think, these two coils, the two partnered output coils, each see themselves as the primary and secondary. Okay, so our partnered output coils are both primary and secondary for each other. Now the time rate of change, which is the delta T of B initial and B final, the delta T of these two quantities is what produces the EMF. So partnered output coil 1, if it's seeing these values, then it's going to have 1400 volts. Partnered output coil 2, if it's seeing the same values, it's going to see this EMF here. Now this is pretty crazy. We definitely don't need to go to that extreme. Let's keep it at a voltage that's manageable, low enough that we can work with properly without doing silly damage and all that sort of thing. Okay, so again, electromagnetic induction is really important. This little calculator is really built to try and help people out. If you want to get to it, on my HiIQ website, if you go into resources and then magnetics and then electromagnetic induction, and you should be able to get to here easy enough. Let's have a bit of a thought picture here, just a sec. Okay, so what we're sort of going to do is we're going to run through and just imagine and try and step through one step at a time as the magnetic fields are changing. Okay, this coil over here has a magnetic field, gold coil here has a magnetic field, and the green coil here has its own magnetic field as well. Okay, the way that I've explained these coils working is, again, the red arrows indicate the magnetic fields. The magnetic field from this coil needs to oppose the magnetic field from this gold coil, so your partnered output coils must oppose each other. If they don't oppose each other, then it's not working. Okay, so if we were to think to ourselves, okay, so this coil over here needs to see this coil over here as its source, and then this coil over here needs to see this coil over here as its source. Now Jagao kindly pointed out that it's resonance electromagnetic induction, and it is, but if you look up resonant electromagnetic induction, you get some pretty weird and wonderful things, nowhere near close to what we're actually doing. However, Floyd Sweet, Don Smith used the term magnetic resonance. I really like the term magnetic resonance because it really truly does indicate, magnetic resonance indicates that there's a magnetic resonance between this coil and this coil. Now for the currents to be equal and opposite and resonant, then the coils themselves must be in a resonant phase as well, resonant state. Okay, so let's separate these two coils for a minute. Okay, and let's say that this terminal is not here, and let's say, as we have been shown by Don Smith.
Okay, you notice that this main coil there has the center part of it cut out, and the two cut things are brought over as your ground deal. Okay, and the ends, the electrons are spinning one direction, going this way, and spin the other direction going that way. So you've got electricity and you've got amps. And when they come together, then it continues on. So you put the two together, and you've got more amps than you know what to do with, and more electricity you know what to do with.
Okay, so let's say, for example, that we had a diode on this end of the coil and a diode on this end of the coil, and there was a load on this coil here after the diode, and there was a load on this coil over here after the diode as well. It just so happened that the diodes were set up so that the currents, if you were to use the right hand grip rule, that the currents could only oppose between these two coils. Okay, so the diodes would be the same as what Don Smith showed us. Now, at any one point in time, a changing magnetic field on this coil must be equal and opposite to any changing magnetic field on this coil, and our diodes are set up in such a fashion that that's what will happen. So any positive change on this coil will induce a negative change on this coil. So both coils loaded must mean that this coil over here will induce an EMF at a time from B initial on this coil to B final, and this coil over here from B initial to B final at the same time. And because our coils are resonant, they will do it over the same time as well. Our coils are the same. So our green coil here must be the signal coil, if you like, for each coil. So this coil here and this coil here. So our green coil here introduces a signal, if you like, into this coil, and that signal will be at a frequency and duty cycle that these coils will start to get excited and start to become, if you like, if you want to use the term, electromagnetically resonant. Now if this coil over here were to be shorted, and if we had a load on this coil, then the time rate of change of the magnetic field changing in time over here would be mirrored by this coil over here if it were to be shorted, but the current flowing in this coil over here would generally probably be just a little bit, I won't say greater, but it would be greater than what it would if it had a load on it. Okay, so if we were to put a load on this coil over here, and say for example that load had an internal resistance of, say, let's say 3 ohms, then 3 ohm the load resistance would reduce the current that's flowing in this coil over here by a factor of the 3 ohms. And remember, I equals V over R. So if we increase R, then the current will reduce. So this is something that we've got to start thinking about. So the change in time between these two coils is important, and remembering it's the change in current, which then the current then creates a magnetic field, and the magnetic field then must oppose between the two coils, this one here and this one here. Now at any one point in time, because the magnetic fields oppose, then the currents must oppose. So we're back to the same idea as what we were talking about before. Effectively, this becomes a non-inductive circuit by its very definition, not closely coupled non-inductive, because closely coupled non-inductive, as we found out in, I think it was video 5, choke the coils off, and we don't want to choke the coils off, so we do need to loosen the coupling. The coupling needs to be loosened between the coils so that our coils can breathe and come to life. If they're too closely coupled, then the coupling, as I say, does choke the induction off, and the induction can't happen. So it's a very, very important set of variables, if you like, that need to be thought about. And again, the factors of the electromagnetic induction between the secondary coil here and the tertiary coil over here, electromagnetic induction between these two coils must be thought about. Okay, we need a wire gauge, we need a cross-sectional area, we need a number of turns so that we can actually try to get the voltage on the terminals as high as possible within reason. We don't want to go silly again. We need to protect ourselves, 10, 15 volts or something like that. That's all you really need to start off with. Just enough to light a globe or something. But this is what we need to start thinking about. So I've seen a few replications out there. Everybody is doing a fantastic job. But a few little things, maybe just try and sort of work with slightly bigger cores. Maybe just try and increase your turns a little bit. Maybe, just a few little things. Just sort of play along. Everybody's getting fantastic results, so I really want to commend everybody. Keep up the good work. This honestly and truly does work. You just need to work at it a little bit. There's a little bit of fiddling. It's a little bit tricky. It's not always easy to get a perfect result first time round, but it does work. Now you remember in my last video I went through and showed a bit of history, and I'll show very quickly again. Okay, so just remember, I showed in my last video, one build-up has produced 100 times more power than was input. So just remember, the mag runs on the same principles. All of these machines, they all run on the same principles. Okay, Terrell Caponese, his device might look completely different, but if you consider the coil here and the coil here, and then Terrell Caponese, how he has some part of the coil with turns wrapped back on themselves, so he has a small part of the coil which is actually non-inductive, which I've just shown. Okay, so part of it has to be non-inductive because that's what pumps the current. That's how we get an excess in current, and that's what we learned in the Mr. Prever experiment. So it all works on the same principles, whether they look a little bit different or not. From Terrell Caponese to Floyd Sweet to the Meg to all of these machines are all working on the same principles. Okay, and just remember that one build-up of the mag produced 100 times more power than was input. But as far as I know, I know of at least probably 3 or 4 different builds that the Tom Bearden team built up. Okay, so play with it, you know, look at your cross-sectional area, look at your turns, look at your wire gauge. Something else I just want to run through quickly in this video. Okay, something that we've seen and talked about before, what I call the rise over run. Okay, now the input coil on these machines is extremely important. The reason the input coil is extremely important is, for the very simple, is electromagnetic induction. Okay, as I said before, all machines will work, but some of them are very much harder than what others are. On very small machines with very few turns, this is what you need to focus on. Very small machines with small cores, small coils, all that sort of thing, with few turns, what you've got to think about is to get a reasonable output, you need to make sure that the coils are being brought up to a maximum voltage. And for the electromagnetic induction to occur between the coils, you need to think about the rise over run, and this has got to be done without saturating the core and all that sort of thing. Okay, so what I mean rise over run is the time it takes for the input coil to ramp the current up fast enough, okay, in the machine so that the input current is the right signal for the output coils to actually do their work. Okay, so if we had, say for example, if we had maybe 10 turns on a 1 centimeter diameter core, then the turns here to get maybe 10 volts, you'd need to see something in the order of maybe a 2 megahertz pulse or something like that. So it'd have to be, again, this is from the minimum magnetic field to the maximum magnetic field, and it's all done over time. Now this is probably not the ideal shot, but if we were to graph time, so say for example time was down the bottom on the x-axis, okay, and up here was magnetic field or current, let's say it's current. Okay, what we need to do is we need to imagine, again, it's not the best graph, but let's just say for example the numbers were to start off from 0 here. Okay, so 0, 1, 2, 3, 4, and so on. And 0 down here, 1, 2, 3, and so on. So we're going to start off here, and what we need to do is we need to get ourselves up to 1, 2, 3, 4 amperes, and that needs to be done in 1 second. Okay, so 0 here and 1. So this is the rise over the run. Okay, so run is the x-axis, rise is the y-axis is amperes, x-axis is time. Now for this to happen, we need an input coil that's only going to probably have maybe 1 turn. Okay, we need to make sure that our input coil is very, very low impedance, very low DC resistance, so that we can push 4 amperes through it as quickly as we possibly can, so that our partnered output coils see a very fast change. Okay, now I just want to play a Tom Bearden video here. Again, just to give you a bit of an idea of rise over run. Tom Bearden used the term rise time and decay time. I'm not very fond of rise time and decay time because effectively this doesn't really work on decay time. It's more of a rise time thing. You need to get the coils, the current in the coils very fast so that you can get your voltage up. But again, not too fast so that it goes stupid. Alright, here's the video.
All of the magnetic field B is now confined to the core. And around that, I've got all the magnetic field energy, the swirling energy that I normally have in every transformer. I've got all of that. I haven't lost anything. But in addition, I've got this extra energy reservoir in space just outside the core. And every time I perturb the core, like with my input coil, I put in, clever devil that we are, we put in pulses, sharp rise time and sharp decay time. If I want to get a little bigger E fields, I make a sharper rise time and a sharper decay time.
Okay, video 10 I'm just going to keep very short. I think we've had some pretty remarkable progress in the last few weeks. I'd like to encourage everybody, keep the progress going please. I think it's very important that we keep the momentum up. If we don't do this, no one else is going to do it for us. Back in the 1920s, as I've already said in a previous video, the US military was working with Lester Hendershot. They had built engines, motors, electric motors, and tested electric motors that could fly aeroplanes that were spinning at 1800 revolutions per minute with no fuel. These motors were running themselves. It's documented on the website. I've put one in the last few posts just a bit up on the current thread. And almost 100 years later, we still have not seen it. Okay, no one is going to do this for us. We must do this for ourselves. If we don't do it for ourselves, we will never achieve what we're trying to set out to achieve. Okay, it will be withheld from us, and nothing will ever get done. So this lies on us. The responsibility is ours and ours alone. We must do this for ourselves, and not only ourselves, but for future generations to come. If we don't do this, it could potentially be lost forever. Some transformer technology that is really the basis of these technologies is starting to be lost already. So if we lose that, then the future of this technology is going to be gone to us probably forever. I'm very serious. Honestly, I really couldn't say this strongly enough. We need to do this for ourselves. Anyway, just want to also shout out to everybody on the forum. Thank you to everybody that's pitching in, helping out, so on and so forth. It's a great help. Thank you very much. Also, if this video helped you, please consider a donation. The links to donations can be found on the website. Please everybody, this is really important. I just couldn't stress that enough. Please jump on board. Please learn it. Please share it. Please get everybody you know involved with it. If we don't do it ourselves, it just won't get done, period.